for additive manufacturing, allowing users to accurately analyze material and parts for production. Ideally, attendees will learn how to use the use of advanced simulation and virtually predict material properties of printed parts and provide optimum print parameters to maximize key build outputs such as density. Okie doke. So here's our agenda today. We'll talk a little bit briefly about challenges and anomalies related to additive manufacturing, mostly focusing on metal, but please understand the technology we present today is applicable to polymers and ceramics. We'll talk about our Genoa 3DP Thermal Management Module, which we like to call TMG, and the challenges it addresses, and addresses those challenges by predicting the thermal history, calculating the melt poo's size, shape, and duration, calculating transient material state, predicting 3D process maps and 3D void maps, and then bundling this information to achieve a particular goal. And as we said in the current example would be driving increased densification of materials. That improved density leads to good quality parts. We'll also showcase the Genoa 3DP software with input and output examples. We'll throw in a little design of experiments optimization slide. And my colleague will come on board, Dr. Nima Mozami, thermal research scientist with Alpha Star, will come on board to talk over a video of the input and output of the software. We'll recap the presentation, and then towards the end, with Jason's help, Dr. Harsh Bade and Dr. Mozami will join us to answer any questions you may have. So, challenges in additive manufacturing, and many of you have been exposed to these, and many of us are racking our brains to adjust and solve them. And many of these consequences of microstructural defects are related to thermal behavior. And so on the left-hand side, you see the phenomena that we address, and then on the right-hand side, the consequences. And nobody wants to deal with intergranular cracks. Surface cracks are not fun. Surface roughness can lead to problems. The pores and voids are fundamental problems. And then issues with net shape and shrinkage are costly because you have to go through a rebuild trial and error process. On top of that, when you throw the fun of residual stresses, oxidation, inconsistent density, anisotropic microstructure, it just results in parts that are not suitable and not acceptable. Fortunately, we have a solution for you. What we've developed over time through multiple research development projects is our Genoa 3DP Thermal Management Tool, again, which we like to call TMG. And TMG, in addressing all of the issues we just talked about, ultimately the goal is to drive toward that quality part, that qualified part, and in this example, driving towards maximum density. So on the left-hand side, we talk about the phenomena that we'd mentioned before, and all of these issues are pretty common, again, thermally related. So swelling is a question of surface tension, melt pool geometry, melt pool characteristics, depth and width of the melt pool. Unfused is the high-speed, low-power settings of your G-code or your build plan. Keyhole is the exact opposite. It's the low-speed, high-power setting. You're overcooking your material. Balling, again, is a lack of wettability on layer to layer. Again, is a function of melt pool characteristics. And then humping is it's just an issue related to, again, melt pool characteristics and size. So on the right-hand side, on the upper right-hand side, you see common control parameters related to the build process. And again, these are things that you have access to as an end user. Ideally, we'd love to open up all of the parameters that a building platform may have, but that might void the warranty. But these are the parameters you can work with, and these are the parameters that TMG can take in as inputs. And then when you're able to put in this information, predict the behavior, kind of see what the results are going, you're getting a sense of what are the problems and phenomena that will be arising on the left-hand side. And then the next step being understanding that, coming up with strategies, optimization techniques to find the ideal settings that ultimately lead to the image on the bottom, the ideal density or maximum density in this particular case. So, what are the capabilities of TMG? Well, it's a multi-phase thermal modeling tool. and it captures all phases of the material, powder phase, liquid phase, solid phase. What does it do? Well, based on advanced physics and semi-analytical formulations, which leads to very fast calculations that are also highly accurate. I mentioned advanced physics. Along the way, it's predicting the entire heating and cooling process. The heating, the melt superheating, the superheat cooling, solidification, sintering, and cooling. The entire process to understand the physics of what's happening during that full process of applying speed, temperature, power. Along the way, it calculates the melt pool size, shape, and duration, length, width, depth. It calculates the transient material states, so it's predicting the density, the volume of solids, the void-volume ratios, factors that are related to material. And with that coupled set of information, it is then able to predict or generate 3D process maps, as well as 3D void maps. So it identifies, most importantly, the safe and unsafe build regions. And you'll see an example of that going forward. But again, based on the inputs and parameter settings, it can give you 3D visualization of where is the ideal settings, good builds, bad build areas, what's the area to apply or input to get the results that you want. And currently, TMG is applicable to these build platforms. Quite a few, both polymer metals applies on both sides. And believe me, if you're interested in working with us to expand this pool in this direction, please step forward. We'll be happy to, again, we're all working together to serve the community. So here, a quick example of outputs. Three-dimensional view of voids, right? And voids kind of also gives you density. Again, three-dimensional output of where are the density issues or density concerns. This is what TMG gives you. Guidance on your build, guidance on your design. Since we have a digital thread, it all rolls together. So let's talk first about thermal history prediction. Play a little video for you while I'm talking to you. So we're predicting thermal history. We're predicting the melt pool, the heat-affected zone. And not only here, you can see in this multi-layer build, it's pointing out to the fact that TMG is working on the first layer of the build and to the 100th layer of the build, whatever it may be. And as you can see here, where we're talking about this blue region, in this particular example, we're talking about the area of powder that's actually melting and cooling, while the rest of it is still in a not melted state because it's prior layers of the build. Again, top to bottom of the build. Please also note that these little element sizes are 25 microns. So every little element here corresponds to a powder. I'm trying to get you the accuracy. So again, as I said, TMG understands the thermal history and the full time scale of the build. It's predicting and understanding what's going on, the heating, melting, melt superheating, superheating cooling, solidification, and cooling. We like to talk about, we'll make a reference to melt pool engineering based on these inputs and parametric settings. But really cool future stuff that will be coming along is really understanding the crystallization. So we can couple melt pool engineering with grain boundary engineering. But that's down the road, but not that far. Trust me, not that far. And as you can see in our predictions of the melt pool size, right, we can tell you at what time step and what particular layer the depth and width of the melt pool is going to be. Let me get out of here. There you go. So again, what is it calculating? I mentioned to you as the build takes place on the micron size, powder elements, you can adjust this. There are visualization settings to whatever you want. You can see here on the far left side, we're looking at thermal history, the heat affected zone. In the central one, we're talking about the dynamic melt pool size. Again, dynamic melt pool size. And then over here, again, material state, voids, void volume ratios, volume of solids, whatever you want to look at and what you want to see. And then this information compiled puts together, in this case, the parameter settings of power and speed versus temperature. It shows you the ideal regions to get the results that you want, the green area, and the areas to stay away from in terms of your parameter settings. Now, the color scheme here says this section is overheating, and this section is, what's it called, no melting, okay? But the point being, it gives you a sense, a visual sense of are you in the right zone. And using my Goldilocks analogy for Goldilocks and the Three Bears, this porridge is too hot, this porridge is too cold, and this porridge is just right. So for the end user, clear, actionable information to build your part correctly and drive towards increased densification, if that's your goal, or ultimately drive toward part qualification. Now, the difference between these two is hatch spacing size. So as you can imagine, right, that the dynamics of the process map change, because we're not just talking about power, speed, and temperature, but all of those parameters come into play. So you get to see and sense how does not just those power and speed settings, but your hatch spacing, any of your other parameters come into play, and how they impact the results. So let's see if we go on to the next page. So why should you trust our TMG software? Who are these guys with their black magic? Well, Generative 3D prediction shows excellent validation with experiment. We've worked with a lot of labs. In this case, results from Argonne National Laboratory. And here they're using thermal camera, the X-ray imaging techniques, high speed. And you can see the close correlation between, that's a good test, right, 0 and 0. You can see the course correlation in time steps between our prediction and the actual X-ray imaging from Argonne. And step by step, as we work our way through the time step, you can see we prove very good validation, very good correlation. And here again, at two different power settings, 340 watts, 520 watts, the accuracy remains in play. And these are results you can get. The whole point of this is a tool that can put in your hands to eliminate the need for trial and error builds and focus on what you need to get done to build a qualified part. Okay, some more examples, more validation in this case. Here we're looking at the output volume of solids, and the significance of this particular slide is a comparison of two different platforms. Here's looking at void volume ratio for a fused deposition methodology and selective laser sintering, both AM processes. But as you can imagine, in this case of your hot goop, your hot toothpaste, once it comes down, it immediately starts to cool. Well, the software still helps you understand what's going on as it cools, layer by layer. At the same time, in the selective laser sintering, it's got to be zapped with heat, and you can imagine as it's zapped, there's going to be a lot of air pockets and voids, and then as it cools, what's the void volume ratio going forward as it cools? So initial porosity of the powder bed, and then what happens with the melting, the superheated melting, the superheat cooling, solidification, all of that is captured. All of that is actionable information to improve your build process. Okay, just a little note. Here you go that the SLS keep a little bit less void volume ratio than our friends over here at FDM. Just a hint. Okay, let's go to the next slide. There you go. So again, a validation example. In this case, we're looking at Inconel 718. We're talking about the fusion, lack of fusion, and then the optimum builds. So let's start over here. As you can see, we built a set of coins, fabricated set of coins, different power speed settings. Here you have the low power, high speed. Down here you have the high power, lower speed, and then trying to find the optimum. Now clearly you can do this process by trial and error, and there's nothing wrong with that. But what if you had a tool that helped you very quickly not only predict these outcomes, give yourself a process map, what's related to these outcomes, right? And then give you feedback based on those predictions about what is a good part and what's going to be a bad part. And what you're seeing here is the increased green section. It shows that you're on track related to the build. And over here, you can see that in the first case where you had the low power, high speed, you never got to the point where you were actually melting stuff. No melting. That corresponds to spirit over here. And then what happens when you whacked it too much? Right here, right? You got the high power, low speed. Well, you overcooked it. You burned that chicken. So what do we have to do to get a better result? The tool allows you to do that. The tool, both standalone or part of our integrated Genoa 3DP solution, helps you get there that much faster. There you go. Change the page. So we talked about predictions and validations. Here's a similar example looking at density prediction. Again, excellent validation against experiment. We talked about a 3DP process map. here's a 3D void map. Again, what gets you the ideal? And of course, based on optimization, there's going to be an ideal parameter setting. But again, either based on your single objective or your multi-objective criteria, that will shift and move around. And as you can see, burned off a bunch of coins, trying to get their sense of what the density prediction would be. And as you can see here, whether it's coin 1 through whatever coin, we're getting very good correlation with test data. Across the board, a couple of outliers there, right? But still very good validation, all high into the 90s. And then from that, we're able to predict what is the ideal power and speed setting for that particular build to get the least amount of voids, maximum density. Again, the tool allows you to do that. Standalone, part of our more comprehensive Genoa 3DP solution. And so, worst case scenario, lots of voids, an intermediate solution, and then the best solution. And as you can see, it comes up and is able to predict that best solution. Okay? And again, it's with the void map that allows you to see, visualize what's going on, where are we going, what are we going. Again, the whole idea here is not only to drive the solution, but give you the visual aids, give you the tools so you can sense a process and you get a feel for this build thing. And so we're trying to eliminate the need for trial and error and have tools that let you do this virtually and get to the result first time, second time, save money on the build, save money on staff, save money on everything. The idea is to make money. Okay, so we talked about single objective and multi-objective. It depends on what you want. You know, you might say, I want all my 10, 12, 15 parameters bundled together with an optimized result. Well, you might be just looking at density. The tool set is there to support that. And so in this particular example, right, trial and error to find ideal density, ran through, came up with trial and error. This is a real example. Their ideal power setting, their ideal speed setting generated 98.69%. And with Genoa 3DP, and TMG, our TMG code, you were able to get the same thing virtually. Eliminate time and error, eliminate trial and error, eliminate the unnecessary costs. Get to that solution virtually, and now you're ready to go without all the problems that you saw in the initial set of phenomena that we talked about, the problems that are thermally related, that trigger the issues that we don't want to see, and ultimately drive the entire process virtually to a qualified part. Okay, so I'm going to talk very quickly about how you input data into the tool, but fortunately my colleague will join us in a second or two with a more detailed explanation and detailed example of what's going on. So first we start with process settings, standard stuff, what's your G-code, build path, what method are you using, you know, from the available list that we talked about. Again, as I said before, you want to help with us expand this list, we need friends and family to do everything like that for this community to keep expanding the tools that are available and support. And then standard inputs that you have. Standard inputs going there, ranges of behavior, directions, time, things that you'd expect. Now, the next input would be the thermomechanical, the advanced physics properties. And nothing, you know, outrageously on the scientific curve, standard stuff you should have. Heat transfer coefficients, densities, initial densities, latent heat of fusion, those kind of things. Excuse me. And any material that you might have in a database, any material that you might have a pre-selected materials that will pop up. Again, a tool, not just asking you to input, but an interactive tool that has access to data that you used before, data that you're currently working on. And think of it also as a mechanism to do quick critical parametric studies. The flexibility of toolset is there for you to optimize not only the results, but your utilization to get the information you need on your build and your design. So once we've got these two process materials, the next input is how do you want to visualize this stuff? And that goes back to the 3D process map, the void volume map, 2D data, 3D data, the kind of stuff you want, basic stuff. And as you can see, we can update that data with basic sets of information, material that you're particularly interested, standard stuff. So it's a very simple process to put together and run. Again, a tool for the AM community, very straightforward, very simple. no massive learning curve, but most importantly, results that you need, actionable information in your hands right away. So it's time to pass this to my colleague, but before I do that, I need to set up the video. So a little brief introduction. We're going to be joined by Dr. Nima Mozami. He's a thermal research scientist. Dr. Nima Mozami, a thermal research scientist at Alpha Star. Alpha Star, small company, small business, populated by a lot of really talented young people who are dedicated to pushing the envelope on AM science, and led by a senior team that really knows the history of manufacturing, whether it's additive or virtual manufacturing, supporting the aerospace, automotive, and energy communities. So I think I need to bring up, wait a minute, it is in this tool. It's already built in, thankfully. There we go. Dr. Nima, whenever you're ready, you can jump in and I'll start playing the video.
Hi, everyone. Thank you so much, Dr. Rashid and Jason, for the introduction and beautiful technical presentation. So today I would like to show you how you can use Genoa 3D TMG module in order to reduce your process qualification, material qualification process. And as you can see, this is the Genoa software platform. And from there, we go to the app launcher. And as you can see in the top tab, we have TMG as well as optimization. So I'm going to go through the TMG input and outputs to show you how easily you can qualify your parts, reduce the trial and error. And on the top side, you can see the G code to CSV conversion. So the CSV file is required to run TMG code. And so definitely you can use the G code for any complex and simple part to convert it to CSV easily. And from there, you can go through the other input parameters, as you can see on the right side. So TMG input on the right, there. So we have three tabs. One is process settings, materials, and visualization, as my colleague mentioned. And here we have different parameters from down there. And, you know, you can change, for example, you have power and scan speed, and you can define different range. On the top right, you see the process methods that we already have available in TMG, such as the laser powered breast fusion, SLM, and other processes. On the top middle, you have browse the print path file, which is related to the CSV file. So you can input the information about the coordinates as well as the speed and power for and layer thickness. And here you can see the range of the scan speed and power. So we need this range to come up with the process map and the void map that we showed in the presentation slide. And this can be run for as many power and speed cases as required. And also, this is not about only the power and the speed. You can examine your inputs for different layer thickness, for hatch spacing, and you can change those parameters to come up with your own process map. So the next tab, okay, so that's the material. And, you know, you can input your material properties, which is melting temperature, initial temperature, the powder bed porosity for the laser powder bed concept, and also other parameters. You can define as many as material as you want. For example, if you have a bottom plate, different material, which we do have, you can add more materials. And also what you need, and important thing is the thermophysical properties, which is density, thermal conductivity, as well as specific heat. And those are temperature-dependent properties that the user can input their own properties, or you can use our available library. And here is the visualization and setting parameters. You can visualize temperature, density, and other parameters. So let's go and have a quick look to the TMG output. We use 3D views in order to visualize the data that we generated by TMG. And for in the TMG mode, you have different things to visualize. We have process map, temperature, void, thermal state, which is the thermal history, all 6 regions that my colleague mentioned in the slide: temperature, void, volume of solid, density, as well as conductivity, and also conduction, convection, and radiation. Okay, let's start with one of them, process map. The most important thing that you need to minimize your defects and find your stable region and get rid of the instability. So here we need 2 files: maximum temperature CSV file as well as the process map CSV file. Let's quickly launch, and now as you can see, you have different regions. You have a stable and unstable. We are looking for the green region in the middle. And we have no melting, as you can see, red region, incomplete melting, falling, overheating, humping, as well as stable. And this is the maximum temperature CSV file that you are using. And by maximum temperature, it means that, that's the maximum value that the TMG predicts during the process for that specific condition, power, speed case. And also, we have the similar 3D map, which is void map, which I'm going to show you very quickly, shortly. And here, let's zoom in and let's have a look to, if you just click on one of these bars, you can see the speed value, which is 300 millimeter per second in this case, and power of 260, I believe, watts. And also the temperature shows 2400 almost, and it is basically showing you the value, and so you can examine the different values from this 3D map. So let's go and take a look at the void map, which is important because those green regions, we are looking for the best answer and best solution, and that is actually the one that has the minimum and least the value for the void predicted by TMG, and that's the micro void. And if you look at this 3D map, you will see that on the top it mentions mean void CSV file, and that's the void percentage. And also, it has the same concept as the process map. The only difference is that it shows you the void value, as you can see in the pink color, and it's for data speed and power, which is in a high power, and it's basically when you have a high energy density, and it causing gas formation, and because of that you're creating the void, and it traps inside the pot, and that's 10% void, as you can see. But in a green, let's focus on the green region. If you look at that, you will see that we have a low void value in that region, and as you can see, it predicts a value of 1.4% for that specific condition, which is I believe around 800 millimeter per second and power of 600. But also, these are, the question is, how can we come up with all those, come up with those two maps? We require other parameters, and those are, we have to use actually, we have to change the input file for the visualization, which is actually one of these binary files for different power speeds. So this is, I'm going to show you other capabilities that's required here for, in order to come up with the process map, which is melt pool, the thermal state. As you can see in this view, you have the different region, heating, cooling, solidification, superheat, cooling, and melting, as well as melt superheated, which when it is overcooked. And then this is the dynamic evolution of all these aspects, like, the thermal state, and then I will show you the melt pool and other parameters. So, and like I said, this is the dynamic. And so we have thermal state, we have the material state, including volume of solid, void, and density. I showed you I'm going to show you the temperature as well, and also we have thermal conductivity and the rest. So let's take a look at one of these parameters. Okay, so this is volume of solid. As you can see, you have on the left side, you have the color-coded bar, and it shows you from 0 to 1. And you can change the spectrum from global range to current range. And this is for, when you are proceeding through the time steps, you can have a better visualization and, in terms of the value. And also, let's take a look at other parameters and data. And so here we have the temperature. And as you can see, you can look at the heat affected zone, and you have the maximum temperature, and you can visualize the temperature range. And also, let's see, we have fused and unfused powder options. So you can click on the fused only, and then just hide the unfused powder surrounded, because this is the laser powder bed fusion. And you can also hide the powder bed to visualize only what exactly laser pass and has enough energy to melt the material. So this is a very good tool to understand how the laser track and laser movement, show, during the process. Also, you can visualize the conductivity, same thing, the density, which is really important here to achieve the fully dense material. And also in the thermalist data, I forgot to mention that you can change the view to melt pool and also examine the dynamic evolution of the melt pool. So I think that this is all for today. I would like to thank you, Jason and Dr. Rashid. I'm going to pass it to Jason. Thank you so much, everyone.
Well, thanks, Nima. I think I got one more slide, which is just a recap. Let me make sure I'm into that, or just questions. But I'll summarize for us. We talked about the TMG. First, we identified the phenomena that are out there with AM fabrication, the macro phenomena that we deal with. We correlated those macro phenomena that they're thermally based or thermally related, and the consequences, the residual stress, the problems with roughness, all of the gamut that we talked about. And we mentioned that we have a TMG code that allows you to predict these outcomes, predict these behaviors based on thermal inputs, based on thermal parameter settings. And then when utilizing the code, not only can you visualize these results, but you can also single objective, multi-objective, pull all those parameter settings to get the ideal build input to get the ideal build outcome. And the example we used was density, but you could go what are the issues that you want and ultimately get the results to drive towards the qualified part. And I guess now I should pass it over to Jason regarding questions.
All right. Thank you, Dr. Miraj and Dr. Nizami. We will now head into the Q&A session. If you have not done so, please, and you have a question for the presenter, please type it into the chat box. I do have a few questions that we can get started with. So our first question is, what type of validation is performed on this software, and how close do the simulated results represent the real-world results?
Okay, so in terms of validation, we do have the melt tool validation of melt tool size, shape, width, and depth with Argonne National Lab that my colleague showed in one of the slides. We do have the validation of the process map showing different regions such as balling, humping, overheating in stable regions, and we validated with the coin UDRI example. And also we had other examples for aluminum, silicon 10, magnesium, Inconel material. We do have validation for Type 64 melt pool. We do have validation for different polymers such as ABS, thermal history of the Walmother University of Dayton. And also, yeah, we do have ABS, PA11, and yeah, other materials involved also.
Okay, thank you. Another question we got is, are there student licenses available to university researchers?
Yes, I believe this is actually something that probably I have to, I think Sarah or Dr. Rashid maybe can answer
Hi,
that
everyone.
question.
This is Sarah speaking. I'm the Marcom manager at AlphaStar. Yes, we do offer different research and academic licenses. So if that is something of interest, please reach out to us and we would be happy to continue that conversation.
Great, thank you, Sarah. So another question here, which are the materials included in the database?
Okay, so the material in terms of, we do, as my colleague mentioned, we do have metals, polymers, and ceramics. In terms of metals, we do have Type 64 aluminum alloys. We do have stainless steel. We do have Inconel 718 and 63, and also for polymer, we do have PA11, PA12, and PLA, ABS. Yeah, and that's all, yeah.
Okay, great, thank you. So this presentation addresses general process settings of a simple melt scan. How can TMG be used to apply to much more complex part simulation with varying thickness, supports, overhangs, etc.?
Yeah, actually, so one of the our breakthrough is, we started from the microscale modeling and also we expanded to macro scale. So this is the multi-scale thermal management code, and you can easily use any complex shape having a G code, or you can use a simple, very simple, simple track of laser movement. And in a complex part, you can consider any complex shapes as long as you have the G code. Then we have the capability to convert to the CSV file and in order to read by TMG. So that's and in terms of the validation, yes, this is something that we can consider calculation of the melt pool thermal history in a micro scale, even when we are considering the macro scale level. So it is in the micron. So that's something that we already considered and also investigated.
Please come work with us to help solve your problem. We'll be happy to look at it.
Okay, we got another follow-up question here. There are sometimes extra ceramic particles that precipitate in the laser bed powder fusion process. Can these extra particles within the metal matrix be modeled?
Actually, that's something we are. Our software doesn't have that capability yet, but this is something that we are investigating to add more feature, and that's one of the, yes, that's true. It's one of the important things, and yeah, it is in development. Yeah.
All right, thank you very much. All right, so I think that's all the questions that we have for today. So if there aren't any more, I'll wait just a second here to see if any more come in. I don't see any coming in. So that will wrap up today's TRX webinar series. I would like to thank Dr. Rashid Miraj and Nima, Sarah, thank you very much. If you have further questions for Dr. Miraj or AlphaStar, please reach out to them directly at info@alphastarcorp.com. It is on the last slide of our webinar, which will be posted on the America Makes YouTube page if you'd like to go back and view it. There will be a post-webinar survey going out to all of those who participated. We do really appreciate the time you take to provide America Makes feedback so that we may continue to improve and strengthen the additive community. And as a reminder, if you think that you or your organization would be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation, or you can reach out to myself, Jason Thomas, at jason.thomas@ncdmm.org. Thank you very much and have a great day.